Number one, we have a box at rest on an inclined plane, and we want to determine the maximum angle that the inclined plane can be at so that the box remains in equilibrium. Now, this problem doesn't intimidate me, and that's because I have security with Newton's second law. I can use Newton's second law to solve almost any problem. And so can you. The net force is equal to ma, but since it's in equilibrium, that means that there is no acceleration. So that means that the net force is equal to 0. Now, we have two dimensions here, so I'm going to break it up into the x and y part. So the sum of the forces in the x are equal to 0, and the sum of the forces in the y are equal to 0. I'm going to call the surface of the inclined plane the x-axis. So I know then that the x part of the weight of the box right here must be equal to the static friction force. And since the angle is going to be a maximum value, we have a maximum force of static friction being equal to the x part of the weight. Now, using trigonometry, the x part of the weight is equal to the magnitude of the weight multiplied by the sine of the angle that we're looking for. So weight x is weight sine of theta. And the maximum force of static friction is equal to mu s, the coefficient of static friction, multiplied by the normal force. Okay, there's the normal force. Now, what is the normal force? The normal force isn't equal to the weight. As you can see here, the weight acts straight down. The normal force acts along the y-axis. The normal force must be equal to the y part of the weight. Where the y part of the weight is equal to the magnitude of the weight multiplied by the cosine of theta. Okay, so this is the weight y vector, straight down is the weight vector, and this angle right here, theta, is the same as that angle there. Now we can combine this equation and this equation to find the angle. So let me take this equation and substitute it into here. So I get weight sine of theta max equals mu s times weight times the cosine of the maximum angle. Notice that weight appears on both sides. So we have the tangent of theta is equal to mu s, where theta is equal to the arctan of mu s. Substituting, we have the arctan of 0.5. Or 26.6 degrees. This is an interesting problem. We have M1 resting on M2, resting on a tabletop. The system is in equilibrium. We know the value of M1 is 1 kilogram, the value of M2 is 2 kilograms, and we're looking for the force on mass 2 due to mass 1. Now don't make the mistake of thinking that the force on mass 2 due to 1 is the weight of m1. The weight of m1 is a gravitational force exerted on m1 by the Earth. Gravitational forces do not push, they only pull. So the force on mass 2 due to 1 is not gravitational, it's electric. So how are we going to figure out the force on 2 due to 1? Well, I'll tell you how. We're going to be using the great law called Newton's third law. Because you see, the force on 2 due to 1 is equal to the negative of the force on 1 due to 2. That's from Newton's third law. So, what we're going to do now is we're going to draw a free body diagram of M1. F12 acts upward on M1. That's an electric force, and it's equal, again, in magnitude to the force on 2 due to 1. Acting downward of M1 is that gravitational force, which I spoke of earlier, M1G. That's the magnitude of the gravitational force. Now what we're going to do is we're going to turn to Newton's second law. From Newton's second law, isn't the net force equal to ma, but since this is an equilibrium, the acceleration is 0. So I'll get rid of this, replace it with a 0. And here we have F12 up, so I'll just call it positive F12 magnitude. And then down we have M1G. So the force on mass 1 due to 2 is equal to the mass of 1 times the acceleration due to gravity. So we have 1 kilogram multiplied by 10 meters per second squared, or 10 newtons. So F21 then is equal to 10 newtons. To many people, this problem is a real doozy. But for me, it's a piece of cake. And that's because I have Newton's second law. In this problem, we're asked to find the force on block 1 due to 2. Now don't make the mistake of thinking that it's just 10 newtons, because this force here somehow is transferred through M2 and acts on M1. So the force on 1 due to 2, since 2 is up against it, would just be this force here, 10 newtons. That's wrong. We're given M1, we're given M2, we know this force over here. We want to know what the force on 1 due to 2 is, and we're assuming no friction. So what I'm going to do is I'm going to draw a free body diagram of M1. And the reason I'm going to do that is because the only force acting on M1 that's going to do anything for us here is the force on 1 due to 2, which is the unknown. The other forces, the normal force and the weight of M1, do not play a role here because they cancel each other out. Remember, M1 is in equilibrium vertically, and because there's no friction. So here is our unknown, F12, which is going to cause M1 to accelerate to the right. So applying Newton's second law, we have F12 equals m1 times the acceleration. We know m1, we're looking for F12, we don't know the acceleration. To find the acceleration, we're going to look at the system as a whole. Then F12 is an internal force and it will not show up in the equation. So let's apply Newton's second law to the system as a whole. We'll do that over here. Sigma F equals ma. The mass is now m1 plus m2. The acceleration of the system is to the right. And this is equal to the net force, which would be the 10 Newton force, which I'm calling F. Solving this for acceleration, we get the force, 10 newtons, divided by the mass, 1 kilogram, plus 2 kilograms. So this will allow us to find the acceleration. Once we know the acceleration, we can take that value, substitute it into here, and we can find the force on 1 due to 2. So let's take this and substitute it into here. So I get F12 equals m1 times F divided by m1 plus m2. So we have 1 kilogram times 10 newtons divided by 1 kilogram plus 2 kilograms. So it looks like the force is 3.33 newtons. The force on 1 due to 2 is 3.33 newtons. Now from Newton's third law, we could figure out the force on 2 due to 1. Wouldn't that be just 3.33 newtons directed to the left? Hello. This is a problem involving a passenger riding in an elevator that's accelerating downward at twice the acceleration due to gravity. It's an express elevator. So we have -2 times the magnitude of the acceleration due to gravity, which we're going to call 32 feet per second squared. And I placed a negative sign in front of it because, again, down is negative. Suppose the passenger weighs 100 pounds. And I'm going to place a negative sign in front of that because down is negative. And we want to determine the apparent weight of the passenger, aka normal force. This is what the elevator rider feels he weighs. So how are we going to solve this? Do you know? Newton's second law. Newton's second law is a very, very useful equation. You should memorize it and remember to use it for most of the mechanics problems we do throughout the course. So what forces act on this elevator rider? Well, one of the forces, of course, is the weight, which I already discussed, and that acts straight downward. Okay, so this arrow here represents the weight, W. The other force that acts on the elevator rider is the normal force, or support force. Okay, and I'm going to show that acting upward on the rider. The summation of these two forces, according to Newton, is equal to the mass of the rider, m, times the acceleration of the rider, which is the same as the elevator, negative 2g. Okay, let's continue this problem over here. What is the net force? Well, it's the summation of the weight and the normal force. The mass from Newton's second law is the person's weight divided by the acceleration due to gravity. Since they're both in the same direction, I can just write the magnitudes. Remember, mass is a scalar quantity. It has no direction. Multiplied by the known acceleration, which is negative 2 times the magnitude of the acceleration due to gravity. So you see, the g's get kicked out of town. That leaves us with negative 2 weight, then is equal to the summation of the normal force and the person's weight vector. Solving for the normal force, we get negative 2w minus the person's weight vector. Now, the person's weight vector, right, is directed downward. So if I take the hat, the vector symbol, off the top of this w here, I have to introduce the direction, which is negative. So I end up with positive w magnitude plus negative 2 times the magnitude of the person's weight. And this leaves us with negative w. In other words, the normal force on the person is equal to the negative of the magnitude of the person's weight. So the direction of the normal force, according to this, is down, and its magnitude is equal to 100 pounds. It's strange, isn't it? Because here I'm showing normal force acting upward. So did I make a mistake? I don't think so. And the reason is because I used Newton's second law, which is 100% correct. And I believe I did everything right here. And as long as I did, and I don't see any mistakes, this must be correct. Therefore, I have to make an adjustment in the diagram. The normal force is down. It's equal to the weight. So I have these two arrows now of equal length. All right, so both the normal force and the weight act downward. So the normal force is exerted on the person by the ceiling of the elevator. You see, the person would have to be like this in the elevator, upside down with his feet on the ceiling of the elevator. The normal force is an electric force pushing down on him, and then you have the force of gravity pulling down on him. It's the normal force that gives this rider the sensation of weight. It's an apparent weight. This is quite an express elevator. If this was had a long enough elevator shaft, after a while this person would maybe forget that he's in an elevator, and as far as he's concerned, he's right side up, living in this room where everything's normal. He could have a pet, like a goldfish, swimming around. He could drink water, no problem. There could be a clock ticking in the background. Okay, here we have a mass 1 with a string attached to it that runs over a pulley, and then we have mass 2 hanging here. There is no friction, that's why mu is equal to 0. The masses are the same, m1 is equal to m2. And this is a single fixed pulley. We're asked to find the acceleration of the system and the tension in the string. Well, Newton's second law tells us that the net force on this system is equal to m times a. So we have sigma f equals ma. What is the net force on the system? Well, the weight of mass 1 is canceled out by the normal force on mass 1. The tension in the string is internal to the system, So that leaves us with the weight of M2 as the net force. So we have M2G is equal to the mass of the system, which is M1 plus M2, times the acceleration of the system. We now solve this for acceleration. So the acceleration of the system is equal to M2, 1 kilogram, multiplied by the acceleration due to gravity, 10 meters per second squared, divided by the summation of the masses. So we end up with an acceleration of 5 meters per second squared. Now how about the tension? The tension is an internal force. So what we're going to do is isolate M1, and then we see that the tension now becomes the net force. So from Newton's second law, we can write sigma F equals ma, where the net force now is T on mass 1, is equal to the mass of the system, which is now just M1, times acceleration. We know the acceleration, we know M1, so we get T is equal to 1 kilogram times 5 meters per second squared, or 5 newtons. What we have here is an Atwood machine. It has a single fixed pulley and 2 different masses. M2 is 2 kilograms, M1 is 1 kilogram, and we're asked to determine the acceleration of the system and the tension in the string, twang. I'm going to begin with Newton's second law. Surprise, surprise. Now, what is the net force on the system? Well, we have 2 opposing forces here. We have the weight of M2 and the weight of M1, which are opposing each other. So the net force will be M2G, the weight of M2, minus M1G. And that will set equal to the mass of the system, M1 plus M2, times the acceleration of the system. Now we'll solve for acceleration, and we get M2G minus M1G divided by the mass of the system, M1 plus M2. So in the numerator here, we have G times the quantity M2 minus M1. In the denominator, M1 plus M2. So we're looking at G, which is 10 meters per second squared, multiplied by the difference in the masses, 2 minus 1, divided by the summation of the masses, 1 plus 2. So we have here 10 times 1 divided by 3, or 3.33 meters per second squared, is the acceleration of the system. Now to find the tension, what we need to do is isolate either M1 or M2. If we isolate M1, then we see that tension is an external force, T, and M1's weight is also, of course, an external force, M1G. So applying Newton's second law again, we have that the net force is the tension minus M1G. Right, the tension is directed upward, the weight of M1 is directed downward. And that's equal to the mass of the system, which is just M1 now, times acceleration. So solving for tension, we get M1G plus M1A. Or M1 times the quantity, G plus acceleration. Mass 1 is 1, the acceleration due to gravity is 10, the acceleration is 3.33, so we get here 13.33 newtons is the tension in the string. This looks pretty similar to a previous problem we had, but I'll tell you what, this is a real doozy. And this makes me very thankful that I have Newton's second law. We have 2 masses, M1 and M2, that have the same mass, 1 kilogram.
And we're asked to figure out the acceleration of the system. Now, notice that there's friction here, where the coefficient of kinetic friction is 0.5 between the surface of M1 and the tabletop. To find the acceleration, we're going to use Newton's second law. So I'm going to write that the acceleration is equal to the net force over mass. Now, what is the net force on the system? Well, we have the weight of M2, and we have the force of friction acting on M1, and this would be a force of kinetic friction because it's sliding. So the net force then would be M2G minus Fk, because these two forces are opposing each other. And isn't Fk equal to mu k, the coefficient of kinetic friction, times the normal force on M1, which is just equal in magnitude to the weight of M1, or M1G. We then divide this by the total mass of the system, which is M1 plus M2. This quotient then gives us the acceleration of the system. So M1 is going to accelerate to the right, and M2 is going to accelerate downward. Let's do the numbers. So the acceleration then is equal to M2, which is 1, times G, which is 10 meters per second squared, minus mu k, which is 0.5, times M1, which is 1 kilogram, times G, which is 10 meters per second squared, all divided by M1 plus M2. So in the numerator, we get 5, and in the denominator, 2. So we get an acceleration of 2.5 meters per second squared. Now, the tension. The tension is internal to the system. However, if I isolate M2 or I isolate M1, then the tension suddenly becomes an external force. I'm going to isolate M2. Okay, so if I isolate M2 and apply Newton's second law, I have here net force is equal to Ma, where the net force now would be M2G, which acts downward, and tension, which acts upward. So I have to sum those two, but since they're oppositely directed, we get M2G minus T equals the mass of the system, which is now just M2, times the acceleration, which we know to be 2.5 meters per second squared. So now we solve this for tension. So the tension then is equal to M2G minus M2A, or M2 times the quantity, G minus the acceleration. So we have 1 times the quantity, 10, minus 2.5. So we have here 7.5 newtons. Notice that the tension, 7.5 newtons, is less than the weight of M2, which is 10 newtons. And that makes sense because you need a net force downward. Boy, I'm sure glad I have Newton's second law for this one. Here we have two equal masses connected by a string, and they're being pulled along with a force of 10 newtons. There's no friction. We're asked to find the tension in the string. We're asked to find the tension in the string connecting the masses. So I need an equation for tension. So Newton's second law, of course. So we have sigma F equals Ma. I'm going to isolate M1. So the net force of M1 then is the tension. That's equal to M1 times A. So to get the tension, really all that I need is the acceleration. Who am I going to call? Newton's second law. So now I'm going to look at the whole system where this force now is the net force. The 10 Newton force is the net force. So applying Newton's second law, again, now we have F equals M1 plus M2 times acceleration. I'm going to solve this for acceleration. And then substitute this expression into this expression for tension. Okay, there we go. So M1 is 1 Newton. The force is 10 newtons divided by M1 plus M2, 2 kilograms. So we have 5 newtons is the tension in the connecting string. This problem reminds me of train cars. There might be a problem that you encounter one day where you're asked to determine the tension and the coupling between two train cars. And this is the approach you would take. This problem involves a car driving along at an unknown velocity. The car brakes and skids to a stop after traveling through a displacement of 20 meters. We're asked to find the original velocity. Now, we know the coefficient of kinetic friction, we know the final velocity is 0, we know the displacement is 20 meters. So I need an equation involving VO. So I'm going to start with the kinematics equation. Vf squared is equal to VO squared plus 2 times the acceleration times delta x. Solving for VO, I get the square root of -2 times the acceleration times the displacement. Remember, Vf goes to 0. Now I need to use Newton's second law to find the acceleration. Acceleration is equal to the net force over mass. Okay, let's draw a free body diagram of the car. If we do, we'll see that the net force is the force of kinetic friction. The normal force, which acts directly upward on the car, is balanced by the weight of the car. So the net force then is the force of kinetic friction, which acts to the left, so it's negative. And the force of kinetic friction is equal to mu k times the normal force. We just saw that the normal force is equal to the weight in magnitude. So I can replace the normal force with mg. So we end up that the acceleration of the car is equal to negative mu k g. This I'll substitute into this equation here, and that will allow me to find the original velocity of the car. So we have VO is equal to the square root of -2 times negative mu k g multiplied by delta x. Substituting in the numbers, I get -2 times -0.5 times g. We just use the magnitude because you notice there's no vector symbol on top of g. So this is just the magnitude of the acceleration due to gravity. So we'll use 10 multiplied by delta x, which is 20. For this, I'm going to use a calculator. I get 14.14 meters per second is the velocity of the car. In this problem, we're asked to determine the acceleration of a mass that is experiencing a force of 10 newtons, and there is friction. So I'm going to use Newton's second law. We know that the acceleration is equal to the net force divided by the mass. The net force would be this force here, directed to the right, so that's why I wrote it as the magnitude of the force, and it's to the right, so it's positive. And I'm going to subtract from that the force of kinetic friction. And we know mu k, and then divide that by m, mass. Now the force of kinetic friction is equal to mu k times the normal force. Where the normal force is equal to the weight in magnitude of the block. Substituting, we have 10 newtons minus 0.5 times 1 kilogram times 10, which is the 10 meters per second squared, the acceleration due to gravity magnitude, divided by the mass, 1. So we have here 5 meters per second squared. This appears to be a fairly simple problem because there's no friction. Since we're looking for acceleration, I'm going to use Newton's second law. We know the mass is 1 kilogram. We need to figure out the net force. These are the two forces acting on the mass, the normal force and the weight. I'm going to break the weight up into its x and y parts, where x is along the surface of the inclined plane. Okay, so here's weight x, here's weight y, and weight x straight downward. So the net force then would be the weight x, and I'm going to call down the inclined plane the positive direction. So we have weight x over the mass. But weight x is equal to the weight times the sine of theta. Okay, here's the angle theta. This is also angle theta, divided by m. Newton's second law again, weight is equal to mg. So the masses cancel, and we're left with the acceleration down the incline as being equal to g times the sine of the angle. Okay, let me do this up here. So the acceleration is equal to g, the acceleration due to gravity magnitude, times the sine of the angle. So we're going to take 10 times the sine of 40 degrees. And I get 6.4 meters per second squared. We say that an inclined plane dilutes gravity. So this box is falling down the incline at only 6.4 meters per second squared. The steeper the incline, the greater this acceleration. If it's 90 degrees, sine of 90 is 1, you get an acceleration of free fall, 10 meters per second squared.